It has been 54 years since humans last walked on the moon during the Apollo missions. NASA's current objective is to construct a permanent outpost, the Artemis Base Camp, where humans will live and work for extended periods. This data visualization compares the near-zero risk of commercial aviation against NASA's own assessment for their next deep space mission, a 1 in 30 probability of losing the crew. Establishing a permanent lunar base requires human-rating new hardware that currently carries a high quantifiable level of risk. To lower those odds, NASA designed Artemis II. It is a rigorous 10-day test flight built to stress test every critical component of the Space Launch System before the agency attempts a landing. 4 astronauts will fly this mission. The crew includes pilot Victor Glover, who will travel farther from Earth than any black astronaut in history. Joining him is Jeremy Hansen, a fighter pilot, marking the first time a Canadian astronaut has left Earth's orbit. These 4 individuals are the ultimate human test subjects. Their flight will validate the systems designed to keep future crews alive in deep space. On April 1st, 2026, those systems face their first physical trial as the rocket breaks orbit with 8.8 million pounds of thrust. This diagram plots the initial launch path. Instead of heading straight to the moon, the crew parks in an elongated high Earth orbit. During this phase, they check environmental life support, practice manual docking maneuvers, and test the capsule's space toilet. Testing these functions close to home is a safety measure. If a failure occurs, the crew can still abort the mission and return to Earth within hours. Once the capsule is cleared, the main engine fires on April 2. This translunar injection burn accelerates the spacecraft to 24,500 miles per hour, committing the crew to the moon. Over the next 3 days of coasting, the crew will rehearse medical protocols like zero-gravity CPR and practice building a makeshift radiation shelter out of spare equipment. This top-down map shows the flight path, a free return trajectory serving as the primary physical failsafe. If every engine fails, the moon's gravity catches the spacecraft and automatically slingshots the capsule back toward Earth. In deep space, gravity acts as a primary rescue mechanism. By April 6th, the spacecraft swings around the far side of the moon, passing between 4,000 and 6,000 miles above the cratered surface. Passing behind the moon means its massive physical bulk will block all radio contact with mission control, leaving the crew in total silence for 41 minutes. As they emerge, they will reach a point 4,600 miles beyond the moon, the farthest humans have ever traveled from their home planet. Operating successfully through this isolated blackout demonstrates that crews can function in deep space without real-time assistance from Earth. On April 10th, the mission concludes with its most dangerous phase, atmospheric entry at a blistering 25,000 miles per hour. Friction heats the exterior to 5,000 degrees. Survival depends on the Avcoat heat shield installed at the base of this Orion capsule. During the uncrewed Artemis I flight, engineers discovered this shield eroded unevenly. They redesigned the system and altered the entry trajectory to ensure a crewed capsule remains intact during the descent. After slowing through the atmosphere, the capsule will deploy parachutes for a final splashdown in the Pacific Ocean, where Navy teams will recover the crew. A safe recovery transitions the Artemis architecture from a prototype to a human-rated vessel. Artemis II connects the heritage of the Apollo era to our pursuit of a long-term presence in space. This mission provides the operational data required for Artemis III, which will attempt the first human landing at the lunar South Pole. Mitigating the quantifiable risks of this 10-day flight establishes the foundation for living on the moon and eventually reaching Mars.